welcome. We continue our discussion on the support vector machine classifier. Let me quickly review what we have studied so far. So, our job was the following: given a training set which is of this form, a set of vectors, in this case 2 dimensional vectors, and their class labels x2, y2, a set of vectors and their class labels. So, in this case we consider a 2 class problem where y can be either +1 positive class or -1 negative class. So, given this training example, our goal is to find a hyperplane in 2 dimensional line of the form w1 x1 plus w2 x2 plus b equals 0. Find a good linear discriminant which will classify the point. So, in this case I have 2 points, the red points and the blue points. The blue points are all positive examples and the red points are all negative examples, negative class examples. So, I want to find the values of w1, w2 and b corresponding to a good linear discriminant. So, if I consider w as the vector of these weights and x as the attribute vector or the feature vector, I can rewrite this as in this form w transpose, w is a vector, x vector plus b equals 0. So, you can extend this beyond 2 dimensions also, all right. So, our goal is to find w and b. So, we observe that in order to find a good w and b, the first thing we need to do is to ensure that the line corresponding to that w and b puts all the plus points in one side, rather the non-origin side, the side in which the origin does not lie, and all the minus points, the red points in this case, in the other side. So, this should successfully do this for all the entire training set. Okay. So, we saw that. So, we the first condition we need is this. Okay. Finding a good linear separator, and then once we find that, what we can do is to actually use the sign of this quantity which will decide which side a point x is in, origin or non-origin, and to accordingly form the class. So, in this side it is actually less than 0. So, it is the origin side actually, and this side it is greater than 0, and on the line it is equal to 0. So, we observed that to satisfy, so what we want w and b to be is that if yi for a training set xi yi is +1, then wt xi plus b, xi is the ith training instant, should be greater than 0. If yi equal to -1, then so this I am basically writing down the condition for correct classification. If yi is +1 positive class, xi would lie on the origin side greater than 0 side. If yi is -1, xi should lie on the negative side. And what we did was to combine these two equations, combine into equations in a single equation which says that the sign of yi and the sign of this quantity should be the same. If yi is negative, this should be negative, if yi is positive, this should be positive. So, in other words, their sign is same means their product is greater than 0, positive quantity. Okay. So, I guess this is clear. So, this is the first condition that we need from our linear classifier. All right. So, let us see. We further observe that there are actually many such lines which satisfy this condition. So, both these lines L1 and L2 satisfy the condition that W t x I plus V greater than 0 all I is the training set or x r max to x n, they satisfy. In fact, if the two classes are separable, we actually showed that there are infinite number of such lines. I can draw as many lines as I want which will satisfy this condition. And what we decided is to sort of not take any line, but take the central line, take the central line. Okay. Take the central line, sorry, yes. So, take the central line because of the fact that maybe the lines which are kind of cornered, they are not good. Okay. So, these two are not a good line, whereas sorry, this two is not a good line, whereas the one passing to the center is probably a good line. The reason we are good in support of the central line rather than this line is that the performance of this central line, let me call it as L1, whereas let me call it as L2, on a new point the generalization performance is better. For example, I have a point here, the central line would still put it into class 2, whereas the corner line L2 would put it in erroneously as class 1. So, generalization is better, and we had a mean of quantifying this corner and the central thing. So, we said there is one quantity which is higher in this corner compared to the higher in this center compared to the corner line. What is the quantity? What we did is with among all these training points, we find out the closest to the line, which one is the closest to the line. For example, this is the closest to the this red line. So, I drop a perpendicular from the closest point, and I call that perpendicular distance as the margin of that line with respect to these points. And then we saw that similarly, the margin here is not is only this much. So, the margin is only this much for this line. We saw the central line indeed has the highest margin among them all. So, if you take another line like this, it will also have a smaller margin. Drop perpendicular that distance. So, we decided that among all these correctly classifying lines on the training set, we will take the one having the highest margin. So, let me come back to this example. So, among all these lines, all these possible line, the highest margin. In other words, you get a maximum margin linear separator. All these are linear separators. We want to take the highest margin linear separator. Let us see how to do that. Let me draw an example and explain you. So, these are my training points. Each of the training point is a pair x I and the class label y I. In this particular example, x I is a vector having two components x 1 I and x 2 I. In general, there can be more components, two dimensional in this case. So, if I consider a line of the form the perpendicular distance from certain x I, let me call this as x I, to this line. What is the perpendicular distance of a point to a line? You remember from your class 12 coordinate geometry, perpendicular distance of a point x 1 y 1 to a line of this form. Let me write down. dxi is nothing but the positive value, absolute value of w1 x1 I plus w2 x2 I. Just plug in these values. Remember, we are looking at the sign of these quantities, now we are looking at this magnitude. Okay, w1 x1 I, w2 x2 I divided by root over w1 square plus w2 square. This is the distance from a point to a line. Let me introduce again the vector notation for this, that will be easier. So, let me draw it. Take a point x I. So, d x I to this line is absolute value of w 1 x 1 I plus w 2 x 2 I plus p So, let me write it in a slightly different vector notation. So, as you remember, I have previously defined W vector to be this pair W1, W2. In general, in higher dimension it will be W1, W2, W3 in 3 dimension and so on, and xi to be this vector x1i, x2i. Then I can write down dx of I as absolute value of W vector transpose xi, the same form I had written earlier, divided by, note that this denominator is nothing but the magnitude of the W vector, the amplitude of the W vector. Okay. It is the distance of the W vector, W is this vector. Okay. So, a notation we introduce for that is this, the norm of W, let me call it as norm W. Okay. In fact, you can write it in a slightly different form also. In fact, if you take W vector and multiply by its own transpose, you take the W vector, multiply by its own transpose, then you get norm of W square, you get norm of W square, right. So, anyway, so sorry, I missed one thing, I missed the B here, please do not make this mistake. I missed the B here. Okay. So, anyway, to sum up, this is my distance from a point to a line, and what is my margin? So, distance is this distance, you take any point, drop perpendicular, take any point, drop perpendicular, drop perpendicular. These are the distances di, dj, d1, d2 and so on, these are the distances. So, can you tell what is the margin? The margin now you can see is nothing but the smallest of these values, the closest point, the perpendicular, the closest point will have the smallest perpendicular distance. So, margin is nothing but the minimum of these distances, the smallest of these distances over all the xi's, over all the xi. Okay. So, that is my definition of the margin. This is my, you note down, this is a very important quantity, is the margin. Okay. And as I have said before, all I want to do is to maximize this margin, find WB, which for a given training set will maximize this margin. So, it is kind of a max min problem, maximize the minimum distance. Okay. Now, I will do a small kind of trick. You look at these two equation of the lines. This is 4. Note that if you examine these 3 lines, they have different values of W1, W2, B, have different values of W1, W2 and B. But are they really different lines? No. Okay. If you plot them, they will turn out to be the same line, and they, of course, if they are the same line, they will have the same margin. Okay. So, which one should I took? Which value of W and B should I took? So, what I will do is the following. I will scale W1, W2 and B by multiplying by some factor. So, the smallest of this value of the numerator of this margin for the numerator, the smallest value of the numerator. So, minimum of this over xi, sorry, capital Xi, minimum of this value. So, see this numerator, for every point there will be some value, for every xi there x1 there will be some value, x2 there will be some value, one of them will be the smallest. So, what I do, I multiply w and b by a constant such that this smallest value turns out to be 1. Okay. This is a critical point you try to understand. It may appear a bit tricky, but you can actually always do that. A very simple thing that we are doing. What we are doing is that I am just choosing a value of w to w. I can multiply w and b by the same quantity. What I have basically done here is that w and b I have multiplied by the same constant and got different values, but they are the same line. Okay. So, I can multiply w and b both by some quantity, so that the smallest this value over all xi's becomes 1. I can always do that. I can always do that. You think a little bit, you take any line, take some point, take some examples, you will see you can always do that. Okay. So, if that is so, then things become very simple for me. Then what I can do is that I will maybe fair up the things a little bit. The numerator of this quantity is independent of xi. So, the minimization I can apply only over the numerator, and I have scaled w and b to make this equal to 1. This entire minimum thing. Okay. So, I can rewrite margin as this. I can rewrite margin as this. All right. So, this seems a pretty nice formula, pretty nice form, just 1 by the slope of the line, 1 by the coefficient of the line, absolute value of the coefficient of the line. Okay. That seems a nice quantity. So, let me summarize, let me again write down the equation of the final way by which we will compute this line. Given the training set, find w and b. Okay. So, what I did, I said that it has to satisfy two conditions, maximize margin and linearly separate. So, I write that find W B such that subject to the constraint the earlier constant, that the sign of y and the sign of this quantity should be same that I had written earlier, should be greater than 0 for all I. This is the first condition we had derived, that all points should be correctly classified, positive points on plus side, negative points on negative side. In fact, I will modify this equation a little bit. If you remember the definition of the margin, we said, so this y is either plus 1 and minus 1. So, it only changes the sign, it does not change the value of this product. This quantity, the smallest value we have said is the numerator of the margin, which we have said can go down to 1, the smallest value is 1. So, this entire quantity will be a positive quantity. Earlier we said it is a positive quantity, now we say it is not just a positive quantity, it has a value, it is positive and its value is above 1. Because this quantity, the minimum of this quantity, the minimum of this much quantity is 1. By scaling W and B, you have already got that. That is why you got the numerator to be 1 here. Okay. So, this is an optimization problem, maximize something subject to some constant. We will solve this optimization problem to get value of W and P in my next lecture. Okay. So, up to this is clear, optimization problems, maximize margin subject to separability, right. So, in my next talk, I end here today. In my next talk, I will explain how to solve this optimization problem. Thank you.